Hi everybody! So in today's video we're going to be learning our first set of rules for finding derivatives so that we don't have to use limits every time. The first rule that we're going to learn is the power rule. So the power rule says that if f of x, if your function, is some number times x to some power, and it could be any coefficient and any power, then the derivative would equal, and then here's how we take the derivative. We're going to drop down the n. So you're going to end up with a times n as your new coefficient times x to the, and your new exponent, you're going to subtract 1 from your original exponent. So it would be to the n minus 1 power. So the basic rule is you drop the exponent and then you subtract 1 from the power to take the derivative. The second rule that you're going to need to know is the constant function rule. So let's say that your function is just equal to a constant, just a number. Then the derivative of a constant would just be 0. Now the reason behind this is that this constant is really a number times x to the 0 power. So when you drop that 0, you get 0 times x to the negative 1, and 0 times anything is just 0. So that's kind of the why that works, and this is the result, is that we usually just say that the derivative of a number is just 0. So let's look at some examples and practice using these rules. For problem number 1, we have p equals t cubed plus 6t squared minus 5/3 t plus 16. So I'm going to take the derivative. Now my notation here is really important, so I'm going to write p prime, because now I'm going to have the derivative. To take the derivative of t cubed, I would drop the 3, leave the t there, and then subtract 1 from the power. So it would be t squared. To take the derivative of 6t squared, I would drop the power. So 2 times 6 is 12. T to the 2 minus 1 is first power. To take the derivative of negative 5/3 t, the invisible power here is a 1, so I would have negative 5/3 t to the 0 power, because 1 minus 1 is 0. And finally, the derivative of 16 is just 0, because that's just a number. Now, we can simplify this a little bit, so we could say that the derivative equals 3t squared plus, now we don't usually write t to the first power, we usually just write 12t, and we usually don't write t to the 0 power because this is just equal to 1, so we would have negative 5/3. And that would be my final answer. Most students will actually just write this as their derivative. They don't go through showing all this work first. And if you're comfortable with that, you can feel free to do that. However, if you want to show the work first and then simplify, that's also fine. Let's take a look at number 2. Now this is a good spot to pause the video and try this problem by yourself if you want to then be able to check your answer and see if it matches mine. So problem number 2, here we go. I'm going to take the derivative, so I'm going to write y prime equals, now the derivative of x to the 4th, I'm going to drop the 4 and change that to a 3 as my power. The derivative of negative 2x squared, I'm going to drop the 2, so 2 times negative 2 would be negative 4x to the first power, and the derivative of 2 is just 0. Now I'm going to simplify my answer, and some of you may have just jumped straight to this answer and gotten 4x to the third power minus 4x as your derivative. One of the things that I think is really important here is to realize that sometimes we have options to use their chances to use the power rule that are not so obvious. Two of those examples would be when you have variables in your denominator or you have rational exponents, which means exponents that are fractions. A lot of times rational exponents look like roots when we write them out in the problem. The first step here is going to be to rewrite all powers with negative exponents or fractional exponents. Then you're going to follow the power rule. So drop the exponent, subtract 1, and finally you're going to rewrite it again into a form that looks a little bit neater and more concise. So an example of a situation where you would use power rule but it's not quite so obvious would be in problem 1. Problem 1 doesn't necessarily look like just a polynomial function like we had up here, but these are still exponents, they just happen to be negative. So step 1 here, I'm going to rewrite my problem. So I'm still dealing with the original function. I'm not taking the derivative yet, so I'm still going to write f of x. I'm just going to rewrite this into a little bit of a different form. So I know that x to the fourth in the denominator means that that's really a negative exponent. So I would rewrite that as 4x to the negative fourth. Then I would rewrite the second term as 3x to the negative third. After I rewrite it, I'm going to take the derivative using the power rule. So my derivative would be, I'm going to drop the negative 4, so I would have negative 16 x to the, if I subtract 1, I get negative 5. And if I drop the negative 3 times negative 3 is 9. X to the, if I subtract 1, I get negative 4. Now you could leave your answer like that. However, most of the time what we want to do is write our final answer with the same type of format and notation as the original. The original did not have negative exponents. They had it written with fractions where all the exponents were positive. So my last step here is going to be to rewrite this one more time. So I'm still rewriting the derivative. I'm not taking the derivative again. I'm not going back to the original function, but I'm just going to rewrite this as negative 16 over x to the fifth plus 9 over x to the fourth. Because since the original problem had exponents that were positive, they were just in the denominator, we want our final answer to match that type of formatting. Another example of a problem where it's kind of a power rule in disguise is number 2. A lot of students don't think about roots as being powers, but it's actually really helpful for us to think about roots as being powers so that we can just use the power rule. So the first thing I would do here is rewrite this function with a power that happens to be a fraction. For example, instead of a square root, I could write 3x to the 1/2 power. Problem number 2, I would use the step number 2, I would use the power rule to actually take the derivative. So the derivative of my function here, I would drop the 1/2, so I would have 3/2, and subtract 1. So I would have x to the negative 1/2. Finally, I would rewrite this back into its original form. In the original problem here, we had a root, not a rational exponent. So I want my final answer to also have a root. Now, having a negative as my exponent means that this is really something that belongs in the denominator with the 2. And having a 1/2 power means it was really a square root in the denominator. And that would be my final answer. All right, thank you guys so much for watching. I hope you have a wonderful weekend, and I will see you for some extra practice.